Good morning, all. Very welcome this webinar on hybrid additive manufacturing. I hope I am audible to all and my screen is also visible. Myself, Amal Raj, I am a project engineer in CDAC, Center for Development in Advanced Computing, Hyderabad. S- About CDAC, CDAC is an autonomous body under my team, Ministry of Electronics and Information Technology. So we mainly do projects regarding cybersecurity, IoT, embedded electronics, HPC, high performance computing, AI, quantum computing, and even now we are into robotics, additive manufacturing, mechatronics, etc. So also we provide 6-month PG diploma courses in advanced computing technologies. So that's about SIDAC. In SIDAC Hyderabad, here we mainly specialize in cybersecurity and embedded systems. So also we have a team on VLSI, quantum computing, and mechatronics. So I am a part of mechatronics team. So I myself have around 5 years experience in additive manufacturing. So before jumping into additive manufacturing and hybrid additive manufacturing, I would like to explain a little bit about different manufacturing technologies, because this webinar we have attendees from various domains, which may not be from core mechanical. So I'll start off with what is manufacturing, and we'll continue after that. Okay. Yeah. So yeah, what is manufacturing? Manufacturing is the process of turning raw materials or parts into finished goods through use of tools, human labor, machinery, and chemical processing. So manufacturing is nothing but if we have a raw material and using some processes, or by undergoing some processes, if we can turn that into a useful or functional item, then that process is called manufacturing. For example, constructing a building is a manufacturing, to be frank. Carpentry is a manufacturing process. Making what you say, automotive parts is a manufacturing, is through a manufacturing process. Even making food in a way is a manufacturing, even though it is cooking. But if you see that mass manufacturing of food items will be there, no? That itself is also a manufacturing process. So generally, manufacturing process should include a tool or human labor or some kind of machinery, or it has to undergo through some chemical processing in order to get the output. Okay. So I hope all know what manufacturing is. Anyhow, I'm going to show you some generally used manufacturing processes here. You can see that the most commonly used manufacturing process is subtractive manufacturing. So I'll explain in detail what subtractive manufacturing is. And the next one is forming. Next one is casting. And one of the latest manufacturing technology is called additive manufacturing. Okay. So first we will discuss about subtractive manufacturing. Subtractive manufacturing is a process by which 3D objects are constructed, successively cutting material away from a solid block of material. So in order to undergo, in order for a functional part to create through subtractive manufacturing, we need a block of raw material. Okay. So from that block of raw material, we will mill out or turn out the unwanted or excess parts and make the functional part out of it. You can see that the material is starting with I want to make a spear. You can see this is a spear. The material is actually a cube box, and it undergoes a machining process, and we will get a final product out of it, and we'll have a wastage of material as well. Okay. Yeah. And that is subtractive manufacturing. Examples are milling, turning, drilling, etc. Okay. So there are, I am just explaining about few, only 4 commonly used manufacturing processes. There are many more manufacturing processes, but I am not going to explain that. Just for your understanding, I am explaining commonly used one only. So if you go, you can see next one is forming. Forming is the process by which 3D objects are constructed through mechanical deformation. So the 3D objects are undergone plastic deformation through some hydraulic punch or something like that, and it is deformed to get a functional part. Okay, so the main example for forming process is nothing sheet metal works. Okay, so where you can see your computer cabinet enclosures are made, even some of the automotive parts, and most of the electronic enclosures are made out of sheet metal fabrication. And even you can see the uh, truss roof will be there, right? In that, aluminum roofs are made through forming, and even some of the mass manufacturers material are made out of forming. You can see that. And here, actually, what happens is mostly there won't be any huge wastage of material. Here, actually, whatever part, if we have a raw material into the desired cut shape, then we can deform that even without any wastage of material. Okay, so but the limitation of forming is we cannot handle complex parts, so we cannot do undercutting, we cannot even say do an angle which is more than 90-degree into a formed shape in some cases, but we can make always special tools. But yeah, the tooling cost included for forming is way high. So yeah, that is forming. So the next one is casting. This is mainly meant for mass manufacturing. So whenever you want to make a material, and you have to say you have made a product and you have made prototype and all, and it is a success, and you want to jump into a market and it need to be massively produced, then you have to choose casting, because that is the most cost effective part, cost effective manufacturing process. Sorry. So the process by which 3D objects are constructed by pouring liquid material into a mold, which contains a hollow cavity of desired shape and then allowing it to solidify. So in case of metal, what we will do, we will melt the metal part, and we will have a mold which will have the desired shape of the functional part, and we will pour the molten part into the mold, and we will allow them to solidify. So mainly all mass manufactured plastic items are made out of mold. That process is mostly called as injection molding. And even the metallic parts, when that mass manufacturing is required, then we will use casting or molding. Okay, so here also there are a lot of limitations. We cannot make complex shapes out of molding. It is very difficult. Uh, and even for a smaller amount of parts, say consider if you want to make less than 100 or 200 amount of parts, the tooling cost required for making a mold is too high. So you have to make, you can see there is a upper part and a lower part, and this part has to be machined, and the tooling, this is called the tool. Okay, so that tooling cost required for a casting required to make a part through casting is too high. So for it is only justifiable when the requirement is more than 1,000 or so. Okay, so yeah, so next we are going to additive manufacturing, also known as 3D printing. Okay, so 3D printing is a process by which, same like 3D process, 3D objects are created by depositing raw material layer by layer with the help of an energy source and solidifying with the help of a cooling source. Okay, so here you can see there will not be any block of raw material usually. So we will start off with zero. Actually, the build platform, you can see this will be the build platform or substrate in case of other technologies. Say there are around 7 technologies also that I'll explain later. So in case of additive manufacturing, what happens is the material is melted or say undergone fusion or something like that, and it is deposited layer by layer, and then it is cured or solidified using a cooling source. Okay, so in general, if you search for additive manufacturing, you will be able to see mostly a technology called FDM. so or FFF, so fused filament fabrication. In that mold plastic filament is feeded into a nozzle, which in which that nozzle, you can see this is actually an example for FFF only. So anyhow, this is not the only technology. There are 7 technologies, but anyway, I'll explain that. In FFF, there will be a filament. You can see that, and there will be a heating element. You can see here. This is a heating element, and that heating element will heat the filament, and it will melt the filament, and it is then deposited layer by layer. Okay, it is deposited layer over layer to get the functional part. So the advantage of additive manufacturing is mostly we can make any kind of complex parts as compared to other manufacturing technologies. Okay, and you will be saving lot of materials as compared to other manufacturing technologies in additive manufacturing. Okay, so next we are going into classification of additive manufacturing process. So as I said, as per ASTM, American Society for Testing and Materials, there are around 7 classifications for additive manufacturing. The first one is material extrusion. So most of you, if you are heard about additive manufacturing, most of you would have seen only material extrusion. Material extrusion is nothing but like a filament is passed through a heating nozzle. That filament it will be melted, and the melted molten material is poured layer by layer onto a build platform, and that build platform is lifted. Either the nozzle is being lifted, or the build platform will come down in order to create that functional part. Okay, so the next one is this is actually most commonly used, and FDM is the most cheaper solution available as of now. But the application is limited to prototype level because of the finishing, and there is anisotropy in mechanical properties. So the material extrusion is limited to mostly prototyping and just to see the look and feel of any item you are making. Okay. So the next one is sheet lamination. So sheet lamination is one of the old technique, which is known as which is just sheets are being cut in the shape of layer, and it is stacked one layer upon another, and it is joined using ultrasonic or some other kind of energy sources. But it is very hectic, and now this technology is actually out of scope. No one is using this technology. This is one of the older technology which is mainly used to make what you say metal parts. Okay, metal parts. So material extrusion mostly we use for polymer parts. Okay, so the next one is vat polymerization. If you see, sorry, I'll go this side. Next one is binder jetting. Binder jetting is nothing but we will have some binders which will be in the form of resins. So that is being sprayed, or first it is atomized and being sprayed into the desired shape, and then it is cured in order to get the printed part. Okay. So the next technology is vat polymerization. Vat polymerization is one of the initial, the first 3D printing technology which was invented. In that, SLA is the first 3D printing technology which was invented actually that time in 1984. So in SLA and DLP, actually the material is resin, and that resin is subjected to a energy source either by the form of, in SLA it is a laser, or in DLP it is light. So that it will be actually photopolymer. That resin will be a photopolymer when it is subjected to a specific wavelength of light. It is going to solidify. So in SLA we will use laser to solidify, and in DLP we will use sorry, so laser to what you say yeah, solidify, and in DLP we will use light to solidify the part. Okay. The next one is powder bed fusion. Here the material will be in powdered form, and here the energy source again it will be either a laser or an electron beam. So there are two technologies, SLM and EBM. This is mainly used for metal additive manufacturing. So vat polymerization, material extrusion, binder jetting, these are mainly used for polymer, and powder bed fusion is mainly used for metal additive manufacturing. So in that, here actually the powder material is subjected to a laser beam, and that laser beam will sinter or melt the part in order to and join in order to create the desired shape. And again, another layer of powder is being poured onto the body, and then onto the build platform, and that is again being exposed to laser, and it will melt the part and join like that it will come. Okay, so SLM has one of the most one of the least anisotropies, because the mechanical properties we will get close to what we will get on subtractive manufacturings like that. And it is very widely used in automotive, to say medical, like mainly in orthopedic domain, and in aerospace, etc. Okay, so the next one is material jetting. Material jetting is somewhat similar to binder jetting only. So here actually uh, the resin is being sprayed into desired shape, and it is being cured later. Okay, so direct energy deposition is one of the cheapest metal additive manufacturing technology, which is the seventh one. In direct energy deposition, actually you can understand, you can see what happens in welding, right? We will have we will have some kind of a feeded fused material which is going through a roll, and it will come through that either it will be a stick that will have some flux and all, and you can similar to soldering and all. So actually that material is being melted using a laser or a like nozzle with uh, some kind of uh, heated element or some thermocouple or something like that, and it is being poured into a build platform. Like instead of joining two parts together, that metal is being melted and poured layer by layer in order to create the functional part. Okay, that is called direct energy deposition. But the defect of direct energy deposition is we will get very less accuracy, because we cannot create very minute or very fine layer parts using direct energy deposition. Okay, so yeah, and next we are going to, in between, if anyone has any doubt or if anyone want to ask anything, you can always stop me and ask. Okay, and even there is a chat box, so you can use that chat box as well. So yeah, AM evolution, additive manufacturing evolution. So first, in 1984, the stereolithography technology was founded, and in 1986, the first 3D printer was patented. And in 1989, a company called Stratasys commercialized the first fused deposition modeling FDM. That is one of the most commonly used printer as of now. Printer technology as of now, not printer as it is, for the prototyping making, and very cheaper. Actually, even it is available in 16,000, from 16,000 now. And that FDM later, it is also known as FFF, fused filament fabrication. FDM is a patented, like copyrighted technology for Stratasys, but the same technology is known as FFF for other machines as well. And as of now, we have around three fused FDM machines in our facility, and one among them is actually from Status itself. Yeah, and in 1992, 3D Systems, a company called 3D System, commercialized first SLA printer. See, in 1984, it was invented, but the commercialization of that printer was happened only in 1992 because of the complexity of uh, the systems involved, because you need a laser source, you need resin beds, and you need typical build platforms, and you need curing chamber, and you need cleaning chamber as well. So the process involved in SLA is a bit complex as compared to FDM. Okay, Actually, the process involved in all 6 other technologies are a bit complex than the process involved in FDM. Okay, so in 1995, Fraunhofer Institute developed the first SLM machine, which is meant for metal additive manufacturing. Now there is a company called SLM. They are very uh, they are one of the monopoly in SLM machines. It's a German-based company, and in 2001, EA has commercialized the first SLS machine. SLS is nothing but similar to SLM. It is like powder bed fusion only. But SLM is mainly used for metal, and SLS is used for polymer parts. Okay. And in 2002, a company called Acram commercialized the first electron beam melting machine. And again, Acram itself in 2007 made first orthopedic part and got certified. So they made a knee joint out of EBM, and they got certified using a material called titanium, and they got certified, and even it was used in a surgery. Okay, so in 2010, a company called Organovo produced the first 3D printed human blood vessel, and in 2013, the first 3D printed robotic human heart also was produced. In 2016, even mass production of 3D printed parts in automotive industry also started. As of now, even you can see if you go to a mechanical R&D institution, they will all have a 3D printing facility so that they can immediately realize whatever design they made before going into a manufactured solution or a functional prototype. They can always check the fit and fit and feel, and they can check the aesthetic, and even they can check the ergonomics, everything in within a fraction of time as compared to the actual manufacturing time required for that prototype to be made. So it eases the design process very well, and it eliminates most of the risk involved in making a functional part using mechanical design. Okay. So yeah, if you go to AM process chain is nothing but the process involved in making a 3D printed part. So mostly it is general to a it is similar to a uh, generic manufacturing process, because there also we need a CAD model. You can see generation of a CAD model. Then we have to convert that CAD model into an AM acceptable format, AM machine accessible format. AM is nothing but additive manufacturing. We just abbreviated that. And mainly that acceptable format is STL, or even OBJ is accepted, and some printer, even IGES is also accepted. But the most commonly used file is a tessellation file called STL. Okay. So first we will convert that into an AM acceptable format. Then we will use a slicing software. So first I said we will have a CAD software. So I'll show you just, I have a CAD software called SolidWorks. You can see this is a CAD software in which I can make mechanical parts. So I'll make a small cube here just to build the curiosity. So here I am making 100 mm by 100 mm cube. You can see. So see, this is actually a CAD software in which I made a cube. Okay. So similarly, if you see, yeah, I made a cube here, and again, if I go back to the slide, you can see there will be conversion of CAD model into an AM machine acceptable format. If you have a CAD uh, if you have a CAD software, you can directly convert from the CAD software to an 3D printing acceptable format. In our case, I am converting it into an STL. I told you it is a tessellated file. It is an STL format, so I am converting that into an STL format. I'll make it cube, name it as cube, and I'll convert that into a file. You can see it's a cube. So it is being saved as a AM acceptable format. And again, there are other machine setup is involved. Before that, actually, in conversion of CAD model into an AM acceptable, AM machine acceptable format, in that first part tessellation that we did, now the second part is slicing. The slicing is actually done using another software called slicing software. It mostly come proprietary to a machine you are buying. Mostly it comes proprietary to the machine, but there is a very commonly used open source software called Cura, which is, I'll show you again. So you can see this is an open source software called Cura. In that, we have a printer called Ultimaker S3, which is a company actually very universally used additive manufacturing machine. And in that, I will upload the model whichever I made. You can see the cube one. You can see that model is being uploaded, and you can see there are some print settings. You can see that, right? So whatever infill I require, whether support is required, whether print addition is required, and even there are, if the part is for visual purpose, or if the part is for engineering purpose, or the part is just a draft part which you just want to see the dimensions, and also according to that you can make the part. Say if I am considering for visual and if I want support and all, I am going to then you do set the parameters. You can see there are again multiple 200 300 parameters, but we need a complete dedicated day session for this to explain. Just I am explaining a little bit only. So you can see that when I am slicing the part, it is showing it requires 1 day and 18 hours to print this entire cube. Okay. And if you preview the cube, you can see this is actually how the printed part will look. If you go inside that, see, this will be the infill density. Okay. So if you increase the density, the size of the triangle inside will also decrease. And if you decrease the density, again, it is going to change. Okay. So then again, what you have to do is here you can see I will have a printer which is connected to a network, and I can give the print directly from here, and it will start the printing. Okay. So before printing, so as I said, first we have done the tessellation and we have done the slicing as well. And now we have to do the machine setup. Okay. So machine setup is nothing but loading the material into the machine, cleaning the blade platform, calibrating, etc. Okay. So that also done. Then the CAD model is being printed. Okay. That we also have to closely monitor. Sometimes when failures may occur, and there are a lot of failures like print warping, and even sometimes the material gets stuck and the temperature parameter might mess up the molten the properties of material. Also, even the material might get caught by moisture, and that also will make the material brittle. So that is generally in case of polymer. Generally, in case of FDM, in metal parts, there are other factors like impurities and anisotropy, etc. So then we will print the part. Then part we have to remove. Then there will be post processing. So these processes, generation of CAD model, conversion of CAD model, and machine setup are generally called as pre-processing. The CAD model printing is nothing but the 3D printing part, and part removal and post processing is commonly known as post processing only. So in post processing, we will remove the support. We will we will finish the parts like using sandpapers and buffing tools, etc. And even we can go for painting and paper smoothing according to your requirement. Even if it is in metal, you can go for anodizing, tempering operations like that. Okay, that is AM process chain. So actually, I am just touching in the surface only, since I'll explain. Like we have several options. If you are interested, you can. I'll show you some options from where you can learn these things. Okay. Now we are going to hybrid methodologies. So as the name suggest, hybrid is nothing but combination of two. Okay, combination of two processes which will effectively get the functional outcome. Okay, so you can see Generally, it is not hybrid additive manufacturing. I'm saying about hybrid manufacturing methodology, just hybrid manufacturing. Okay. In that, first one is milling and turning. You can use a subtractive manufacturing machine as well as a additive manufacturing machine to get a hybrid machine. Similarly, you can get some laser assisted machine processing, vibration assisted machine processing, electron chemical grinding, and ECAP extrusion. These are all different kind of manufacturing processes to get a hybrid process. Okay. Then you can use different kind of materials, like composites. You can use carbon fibers. You can use composite layer printing. These kind of different materials in a single part used as a hybrid material or structure or function. Okay. So these are the three hybrid methodologies. Either it will be a hybrid machine, or can go through hybrid process, or it will have a hybrid material and structure or function. Okay. So how does hybrid manufacturing work? So one of the most common methods used in hybrid manufacturing is to, as I said, additive and subtractive processes in sequence. So it's actually nothing. Say when you are consider you are making a part, and if you are using a milling machine and turning machine, even that is a hybrid process, but it is coming under subtractive manufacturing. Say if you are making a part out of casting and then machining it out to get the finishing, then that is also a, but it has to be combined together. It is not like it has undergone casting first and taken from there and went to a subtractive manufacturing process and you have machined it. That is not like that. It should happen all together. Then it will be a hybrid process. Okay. So it is also typically possible to alternate between additive and subtractive. This anyway, we are going to discuss about hybrid additive manufacturing. So before that, how hybrid additive manufacturing is good or bad, that we are going to discuss. So as I said, hybrid additive manufacturing is nothing but combining a subtractive manufacturing and an additive manufacturing processes together to get a better efficient outcome. Okay. So why do we need hybrid manufacturing? This is actually not hybrid manufacturing, hybrid additive manufacturing. Okay. So if you see this chart, you can see the price of the part, and you can see the material subtracted by the material subtracted by the part, and in one material added by the lens. Nothing. The one process shows the subtractive additive manufacturing process. Sorry. The second one shows the additive manufacturing process. So in subtractive manufacturing process, if you see as the machining being subtracted, like if the part milled out or the wastage which is coming out of the milled part is more, then the price will increase. You can see that in red, right? The price is increased when the subtracted part is more. Okay. But in case of additive manufacturing, if the subtractive part, if the added part, money, if in case of subtractive manufacturing, additive manufacturing, if the added part is less, the material density is less, then the price will be less. And if the added part is more, then the price will be more. You can see that here the subtracted part is more, then the price is more. If here the added part is more, then the price is more. So actually, if you see, if you combine these things, you will get the advantages of both, and you can make the parts more efficiently. That's what this graph depicts. And if you see the system, now I am going to explain what hybrid additive manufacturing in detail. So if you see that hybrid additive manufacturing, the combination of subtractive and additive manufacturing, as I explained earlier, hybrid systems are most often consist of a machine tool. Either it will be a turn center, it might be a milling machine, it will be a lathe, a robotic arm, or anything, a 5-axis CNC, something. And what happens then, we will use a deposition nozzle, whether it will be a DED nozzle or it will be a powder bed fusion machine. So using that, we will combine additive and subtractive manufacturing processes, and we'll get hybrid additive manufacturing machine. Okay, you can see this is an additive process and this is a subtractive process. So I'll show you a video where a company called Masak and Seco.
For the past several years, we've worked in collaboration with Masak
I hope
and
the
Seco.
audio is
More
clear.
recently, we've worked with them to accelerate the adoption of hybrid manufacturing by demonstrating the latest machine tools, the latest tooling, and the latest software for this technology. Today, we're demonstrating an aerospace component. Today, we're demonstrating an aerospace component. Typically in aerospace, the components are made out of high-value materials and materials that are quite difficult to process. These materials tend to come in large billets, and then we remove a lot of that material to get to the final geometry. This obviously takes a lot of time to machine, and the material is quite costly to begin with. Hybrid manufacturing offers the opportunity to reduce the waste material and also reduce the cost of machining.
The machine behind me is a Variaxis J600 5XAM. It's a full 5-axis vertical machining centre with the added capability of additive manufacturing. The block itself, which is the hub, we use an Inconel 718, and to build the blisks themselves using the Inconel 625. So using this material can be quite challenging when you're trying to machine things. You have to run things quite slowly with small depths of cut. This costs a lot of money in machine time as well as tooling. So the great thing about this technology is building the net shape, so you have a lot less material to be cutting.
Hybrid manufacturing has several challenges. One of these challenges is around managing heat input into the process. So heat input in the process leads to a lot of internal stress in a geometry. And this can lead to distortion of that geometry, or in some cases, cracking or failure of that component. So for this project, we've used two different Autodesk products. Firstly, we've used the power of Fusion 360 to create the CAD model for the geometry. In conjunction with that, we've also used Fusion 360 to create what we call the deposition. So used CAD model for the geometry.
Manufacturing. The block is in machine time as well as tooling. So the great thing about this...
Firstly, we've used the model for the geometry. In conjunction with that, we've also used Fusion 360 to create what we call the deposition model. And this is a geometry which is slightly larger than the CAD model that represents the additive deposition. Once we've finished in Fusion 360, we've then taken that geometry into PowerMill. Now in PowerMill, using the PowerMill additive capability, we're able to create the additive toolpaths to drive the metal deposition process. Then, also being in PowerMill, we're able to create the machining toolpaths to reveal the final components. Using Autodesk NetFab simulation utility, we have the ability to simulate the additive component of the hybrid process. This allows us to see heat inputs, internal stress, and distortion within a component during the additive process. This information can then be used to make changes or inform decisions on how we deposit the metal.
So hybrid manufacturing is coming more and more to the fore, and it's something as a subtractive manufacturer we could have shied away from, but we've actually embraced. And seeing this technology emerge in the market has influenced the design of our tooling. On this demonstration, we have a combination of some of our solid carbide offering, and in preparation of this demonstration, also some of our advanced material tooling, essentially ceramic inserts. So we've looked at putting tools on there that offer great tool life and stability and resistant to damage caused by the rough surface, whilst also still offering productivity and stability.
So one of the great things about this demonstration is we can show the user that this machinery is commercially available. We've got great cooperation with our partners. Such
Here
as
you can
Autodesk
see
and
that, right?
Seco. Everything
This
is
is
available
the
on the commercial.
this is the added part, and they are whatever item you want to make, you have to make a little excess, and you have to machine out the remaining part. Okay.
Basis. We have enough research and knowledge now that we've developed over the past few years with our partners that we can take a customer's project and move it
You
forward.
can see it looks like it will be similar to welding, but you will have better finishing than welding.
And use additive manufacturing to the best of its ability.
So you can learn more about Autodesk manufacturing solutions by visiting autodesk.com.
Okay. Yeah. Then I hope you understood what hybrid additive manufacturing is. So here actually, if you know what is buy to fly ratio, buy to fly ratio is nothing but the final product weight as compared to the initial raw material weight. So actually it is a general depiction of how efficiently you are using your work, the raw material, and how much wastage is being produced. Okay. So if you see that in conventional processes, buy to fly ratio is almost 9:1. So almost if you in general, it is not about a single part. So they have conducted a large study and they found out a solution that if one is the weight of the functional part and nine up to 9, say 1 kilo, if the weight of functional part 9 kilo is being wasted as a material waste. Okay, wastages. But in case of a hybrid additive manufacturing process, it is again very less. Only additive manufacturing, it is very less. But in case of hybrid manufacturing process, buy to fly ratio, again, instead of starting from a solid block, you can just take a rectangular, a cylindrical pipe, and you can start building the flanges using an additive manufacturing. There it will be the cost will be the byte fly ratio will be around 2:1. Okay. Then again, if you see the quality also, the quality is actually in case of mechanical strength, I'm saying, say if you are using a technology called direct energy deposition, there is often a chance for anisotropy. Anisotropy is nothing but the inequality in properties in z direction of a mechanical part. Directional inequality of mechanical properties in a solid part is called anisotropy. Inequality, not equality. So it should be equal. It should be homogeneous actually. So it is not that. So the quality improvements are being made when it is undergone through quality, and precision improvements are being made when it is undergone through a subtractive manufacturing after an additive manufacturing process. Okay, so these are some components which is made through both hybrid additive manufacturing. You can see some blades. You can see this blade. Inside that, you can see a honeycomb kind of a structure. That kind of structures can be only made through what additive manufacturing, right? Then the outer surface is being finished using a subtractive manufacturing process. Similar to that, you can see a injection mold items, some pipes. Conformal cooling is one of the main example of combination of additive and subtractive manufacturing. Drill bits, turbine housings, okay. So if you see the classification of hybrid AM machining processes, so you can see if the energy source is laser, we can use laser welding and machining, where AM process will be a direct energy deposition module, and here the material feedstock will be powder, and the type of material mostly used is metal. And there is a laser cladding and milling process here also. AM process is DED, and milling is nothing but machining, but it might not have all the access operations. So again, laser welding, laser cladding, and laser deposition all will have a deposition nozzle, and technology will be DED, direct energy deposition. So next one is SLS and milling. So here powder bed fusion, like will be the AM process, and again CNC will be the subtractive manufacturing process. Okay, and the next one is plasma arc welding processes are there, right? So here again we will use arc welding technologies like 3D welding, plasma, micro casting and solid state fusion that we will use. Here also the AM process category is DED. I told you in the beginning itself, welding is actually a direct energy deposition. Only PBF is different. Most of the mechanical additive manufacturing technology falls under DED. Okay. Then next is solid state fusion. In that, nothing sheet lamination, ultrasonic welding. We will stack sheets of different layers and we will use ultrasonic welding, and then we will mill out the functional part. But this is very rarely used because sheet lamination is an outdated technology. Then again, layer compaction manufacturing, again nothing powder bed fusion, milling and sintering. Sintering is nothing but a fusion process. In SLM, selective laser melting, the laser is used to melt out the part, but in sintering, the laser is used to not melt the parts, just to fuse the part and join together. Okay, so this is mainly used in ceramic items. Okay, so now I want to show you a machine tool configuration of hybrid additive manufacturing machine. So here you can see that there are 4 types. In that, one is turn mill, where you will have a ATC. ATC is automatic tool changer. In that, you will have an additive head like this. You can see that, right? And you will have a subtractive head. Sorry, you will have an additive head like this, and you will have a subtractive head like this. Okay. So these are being changed and used here. It is same in case of a 5-axis milling machine combined with an ATC and an additive head. And there are other permanent mounting options as well. And either you can use a robotic arm, which consists of a nozzle head, and you can use a subtractive manufacturing machine separately. So the advantage of one, now the industry is looking forward most to this kind of a technology where the additive head is fixed to a robotic arm. Why? Because when it comes to maintenance and servicing of parts, say consider in case of a large turbine, a small turbine blade portion is being broken. Okay, so if there is no option for additive manufacturing itself, then we have to dispose the material and we have to buy a new one. But since the additive manufacturing option is there, it is always better to get an additive manufacturing machine at the location where this turbine is being fitted, and turbine blades is being fitted, and made the repair there. Okay, so that transportation hassle will be less. So in order to handle that, in order to have that flexibility, nowadays the hybrid process is generally incorporated with a robotic arm. Okay, a robotic arm is being fitted with a deposition nozzle, and even nowadays, even that robotic arm is made to be in such a way that it can handle even a subtractive head like a spindle and a chuck hand which is connected to an end mill or drill, something like that. Okay, so now even the research is going on. Some IITs like IIT Guwahati and IIT Kharagpur, they are into this. They are making that. Even IIT Kharagpur even made a robotic arm with the Kawasaki robotic arm and a direct energy deposition nozzle, not the subtractive one, only the additive one. So it is being made as of now, and it will be very useful in the future. Okay, so just I want to show you 2 more videos to show that exact process, how it will be. So this is from a company called DMG Mori. This is actually a complete hybrid additive manufacturing machine, which will have all the parts. Okay. This has a powder bed fusion deposition module. You can see powder is being heated, and in between laser beam is coming. This is how deposition happens. You can see that, right? See, this is another material. You can easily do that also, composite kind of. Now this is a subtractive head, and the open thing, right? This is actually ATC, automatic tool changer, okay? And only the part where the machining is required is being machined. Yeah, and we'll go see one more video. Again from DMG Mori, Laser Tech. DMG Mori is one of the main manufacturer of additive manufacturing and even AM machines and subtractive manufacturing machines both. So they are one of the initial standalone hybrid additive manufacturing machine maker, if you say. So you can see the powder is being deposited. It is being deposited layer by layer. You can see that, right? See? Now the excess part is being removed using a subtractive head. And only where that close tolerance is required, that areas are removed using a subtractive head. Okay. You go further, you can see again layer by layer deposition. If you go further, you can see similar parts are being made. Now see again, veins are being deposited and machined. Okay. So mostly these parts, these items are used in aerospace industries. So when we are going to commercial hybrid additive manufacturing machines, one of the manufacturer is DMG Mori in that laser 1665D and laser tech 40,000D are one of the machine. Anyway, we are not promoting anything, just for your reference only we are saying this. And another company, the beginning we showed, right, Mazak, they are also into hybrid additive manufacturing machines. Okay, so anyway, these things I already explained in the video. So yeah, that's it. That's it as of now. So that's what hybrid additive manufacturing is. In the meantime, if anyone has any doubt, you can ask. Anyone has any doubt or queries, or even you can always use chat box also. I hope no one has any doubt. Anyway, thank you all for joining to this program. And in the meantime, I want to explain a small thing. So there is a, so I hope my screen is visible. In that, there is a website called FutureSkill Prime. I hope you are aware of that. So if anyone wants to deep dive into additive manufacturing, so FutureSkill Prime platform is a very good option. So in that, there is a course being uploaded called Introduction to CAD Modeling and 3D Printing. 3D Printing, which offers in advance to whatever I explained today, a little bit in depth of additive manufacturing technologies and the CAD modeling with respect to that. So here you can find our course. If you go to this is the FutureSkills platform, and if you go to courses, here you can see the domain. If you see the domain, you can see the 3D printing and modeling. And if you search, you can see a course called Introduction to 3D Printing and CAD Modeling. And it is very cheap as compared to other platforms. And you can always use this. This is being developed combinedly by CDAC, NAILIT, and NASCOM and MITI. So this platform is as a part of a digital upskilling program. So you can always use this. I'll share the site detail in chat box. Okay, so you can use this. You can visit the site and you can go through the program. If you're interested, you can always try out the program. And even for government employees, sorry, not for government employees, there is a government official training program as well. So that will be circulated to all the organization. And for other people who are working and who are in job, they can attend this program, and all can attend the program. All who are above 18 can attend the program. But those who have a job in hand, or those who want to change the job, they can always complete the program and avail 50% reimbursement on the course fee on the program. The course will be, the 50% of the course fee will be returned as the completion of the program by MITI. So you can avail that incentive model as well. Yeah, that's all. So thank you all. Thank you all for participating in the program. Thank you.